Chapter 17, sections A and B. I wanted to talk about limits involving infinity. What's the limit as x approaches infinity of 1 over x? Well, obviously as x gets really big, 1 over x gets really small. And so that limit's going to be 0. What if it's slightly more complicated? What about the limit as x approaches infinity of x plus 2 over x plus 3? Well, some common sense could tell you that both of the numbers are getting really big, and the plus 2 and the plus 3 are really negligible as x gets very, very, very large. So we're simply looking at x over x, which simplifies to 1. To be a little more analytic, though, what we could do is we could multiply the top and the bottom of our fraction, of our expression, by 1 over x. Now, because of the properties of limits, we know that we can take the limit of this entire expression will be the limit of each of the individual terms added on top, added on the bottom, and divided overall. So the limit as x approaches infinity of 1, well, 1 is just a constant, so that limit is going to equal 1. The limit as x approaches infinity of 2 over x is going to go to 0. And likewise for the denominator, that limit will be 1, that limit will be 0. So the limit of that expression is 1. This technique of dividing by powers of x can give you a way of analytically coming up with the answers, but a lot of times common sense will also get you there much more quickly. So for example, the limit as x approaches infinity of 4x over 3x squared. Obviously, as x gets very, very large, x squared is going to be much, much larger than just x, and the 4 and the 3 are going to be negligible because the denominator is getting so large. If we wanted to do it the other way, though, and I'm getting sloppy here, but I should write the limit in each of these expressions. And now here, as x goes to infinity, obviously this is going to go to 0. All right, another example here. I'm not going to go through the analytics, but if we just think about this, as x gets really, really large, the minus 4 in 3x minus 4 is going to be negligible. And likewise, the plus 1 from 7x plus 1 is going to be negligible as x gets really large. So what we're really looking at is just 3x over 7x, which is going to be, as no matter how large x gets, it's always going to be in the ratio of 3 to 7. And so that, in fact, is our limit. So we can make these as complicated as we want, where we have a polynomial divided by a polynomial. In this case, because we have x squared terms, the term that has an x in it on top, 7x, as x gets really, really large, even though 7x is very large, 4x squared is so much larger that the 7x is really not going to matter much. And also the minus 2 will have very little effect. So what we're really focusing in on is the 4x squared over 5x squared. And once again, that's going to simply be a ratio of 4 over 5. If you like, you could divide everything by x squared. In each of those terms, the limit as x approaches infinity, those are going to equal 0. So we're left with constants 4 and 5, so therefore we get 4/5. The last example, though, we have an x squared term on top and just an x to the first term on the bottom. So now as x gets really, really large, the top is getting much bigger, much faster than the bottom. So our numbers are getting larger and larger and larger as x gets larger. Therefore, this limit does not exist, but we want to be more specific, and we would say positive infinity. So we have some general rules whenever we're doing the limit as x approaches infinity, or negative infinity, of a function f of x over a function g of x, where f and g are polynomials. So in general, if the degree of the numerator is greater than the degree of the denominator, then our values are getting larger and larger and larger. So our limit is going to approach plus or minus infinity. If the degree in the denominator is larger, then our overall limit is going to approach 0. And if the degrees happen to be the same, then we have to look at the leading coefficients of the highest degree terms. You have to be careful and make sure that you don't work too quickly and just look at the leading terms, because maybe the polynomial will not be in ascending or descending order. So to apply those ideas to a few examples, let's look at the limit of 3x minus 4x squared over 7x plus 2. Here the degree is higher in the numerator, so we know the limit is going to plus or minus infinity. But notice we're multiplying the x squared times the negative 4, so we're going to wind up getting negative infinity. How about the limit of this very large function? 3x to the fourth, 2x cubed minus x squared plus 7x plus 2 over 5x to the fourth. The highest degree term in the numerator is an x to the fourth, and the denominator is also an x to the fourth. So therefore, the overall limit as x approaches infinity will be the ratio of the coefficients of those x to the fourth terms. So we get a limit equal to 3/5. How about this example? If you're in a hurry, you might think negative 7 over 6, but with a little closer inspection, you'll notice I'm trying to trick you here, and the degree in the denominator is higher than the numerator, so that limit should equal 0. And lastly, let's talk about the limit as x approaches negative infinity. Now for this one, we have the degree in the numerator is 3. And then the denominator is 2x squared. So since the degree is higher in the numerator, it's going to be approaching positive or negative infinity. Now in this case, if we plug in a very large negative number for x, x cubed is going to give us a negative value. Then we're multiplying that by a negative 3x, or a negative 3, and therefore our limit is going to approach positive infinity. Okay, a quick note on asymptotes, because limits of infinity are involved here. A line y equal b, where b is a constant, is a horizontal asymptote of our graph for a function y equal f of x if either the limit as x approaches infinity of f of x equals b, or the limit as x approaches negative infinity of f of x equals b. So as we go further to the right or further to the left, if we're approaching a constant value, then that's going to be a horizontal asymptote. How about vertical asymptotes? A line x equals a vertical line, will be a vertical asymptote for a function f of x if either as x approaches a from the left equals plus or minus infinity, or as the limit as x approaches a from the right of our function equals plus or minus infinity. So horizontal and vertical asymptotes. Let's look at a couple examples. If the numerator and denominator of a rational function have no common factors, then a factor of the form x minus a in the denominator will correspond to a vertical asymptote x equal a. So if you're asked to find a vertical asymptote for a rational function like this one, first thing you need to do is factor and simplify. The numerator is the difference of two squares, and the denominator has 4 terms, so factor by grouping is a technique we can use. And notice we have common factors x minus 2 in the numerator and denominator. So our final simplified result is x plus 2 over x plus 3 times x minus 3. Therefore, we're going to have vertical asymptotes at x equals negative 3 and x equals positive 3. What's going on at x equals 2? Now, the original function before I simplified it is not defined at x equals 2 because we get a divide by 0. But as we talked about earlier, when you can cancel factors in the denominator, those are not going to be vertical asymptotes, but those are holes in our graph. So our function is continuous until we hit x equals 2. There's a hole in the graph, and then it continues on after that. Let's take a look at the one-sided limits as x approaches negative 3. So if I go back, to this expression, x plus 2 over x plus 3 times x minus 3, notice as we plug in numbers closer and closer to negative 3 from the left, in the numerator, we're approaching negative 1. And with the x minus 3 term, we're approaching negative 6. But with the other term, x plus 3, we're approaching 0. But as I'm plugging in numbers to the left of negative 3, like negative 3.1, negative 3.01, I'm going to be getting negative values here. So we wind up getting really, really small negative numbers in our denominator, which gives us really, really big negative numbers overall. And so we're approaching negative infinity. Likewise, if we look at what's happening as we approach negative 3 from the right, negative 2.8, negative 2.9, then those values are going to be positive, so we're going to get a negative 1 over negative 6, which is a positive 1/6, but then we're dividing by very small positive numbers that are closer and closer to 0, which gives us a very big positive number. So what's the limit as x approaches negative 3 for this function? It does not exist because we're approaching negative infinity from the left, positive infinity from the right. and therefore the limit does not exist. We can't be any more precise and say positive infinity or negative infinity because it's approaching from two different sides. Likewise, we could analyze what happens at x equals 3, and we'd have to look at the one-sided limits for that. Finding horizontal asymptotes, well, we're looking what happens as x approaches infinity, and we get y equals 0 for the x-axis, because if we go back up to our original function and use those rules that I talked about a few minutes ago, the highest degree on top is 2, highest degree on the bottom is 3, so therefore the limit as x approaches infinity is going to be 0. And so that gives us our horizontal asymptote.